Hello everyone, my name is Abeer and my partner's name is William. We are doing Project 9B and our research title is A Qualitative Study of CNN Optimizers with Weight Decay. In this project, we will be comparing the loss landscape with different optimizers with different techniques and amounts of weight decay. We're using a dataset called Human Faces, and it comprises of 10,000 images of human faces split into two categories: 5,000 real human face images and 5,000 AI-generated face images. We then use this dataset to train a CNN with a function that iterates between different types of optimizers. In the past few weeks, we studied different hyperparameters and their effects on the loss function. Hyperparameters include batch size, which is the number of samples used for each gradient descent update, the learning rate, which is how big of a step each gradient descent update takes, and the weight decay, in our case, L2 regularization as covered in the core stage.
This week, we improved our code by making it more efficient and maintainable by adding comments, structured iteration loops, and other things. To study the results, we plotted one-dimensional linearly interpolated graphs. This method used a parameterized function changing the variable alpha in j of alpha equals the loss of alpha times theta plus 1 minus alpha of theta prime. We chose the range of alpha in the form of x, y, where x meant the output was more weighted towards one set of parameters, theta, and y meant the output was more weighted towards another set of parameters, theta prime. Keep in mind that j of alpha is our scalar objective loss, and is what we plotted on the y-axis compared against the alpha on the x-axis, which in turn showed us the loss landscape between two sets of parameters by slicing a 1D line through it. These two vectors are usually the initial and final parameters, and this would show a 1D path sliced through it. All our models were trained with 20 epochs, a batch size of 256, and a learning rate of 0.01, with the weight decay also set at 0.01. The optimizers were tested in both weight decay and non-weight decay variants.
This week, we also study the effects of decoupled weight decay, and decoupled weight decay is where the weight decay step in an optimizer is applied independently of the gradient update step. A paper we studied showed the terms L2 regularization and weight decay are often confused, as they have the same effect for optimizers such as SGD, but have different effects for adaptive gradient optimizers. This led to the creation of ADAM-W as a decoupled weight decay variant of ADAM. Our preliminary findings suggest that the coupled weight decay ADAM is better than the decoupled weight decay ADAM-W, as the loss graphs had less erraticness between the lines.
Intuitively, when ADAM is run on the loss function f plus L2 regularization, weights tend to have large gradients in f do not get regularized as much as they would with decoupled weight decay, since the gradient of the regularizer gets scaled along with the gradient of f. This leads to an inequivalence of L2 and decoupled weight decay regularization for adaptive gradient algorithms. This was a quote from the paper we just studied. When analyzing the graphs, there are several phenomena to consider. The steepness or sharpness of the local minima, which is the gradient of the sides of the local minima, show us how deep the local minima is. Another thing to consider is the width of the local minima, shown as the line on the graph, how long the line is, or otherwise known as the flatness, which shows how much area does the optimizer have to explore and settle in a good local minima. The erraticness or jaggedness of the loss landscape shows different amounts of convexity at different points of the graph. So a place with high erraticness shows it's really highly unconvex in that place of the graph. And finally, we also studied the effects of decoupled weight decay versus coupled weight decay for the ADAM optimizer. The differences can be said based on the previously mentioned phenomena as described before.
Overall, when we trained our models with different optimizers, we got some interesting results. Our optimizers in question are SGD Momentum, RMS Prop, AdaGrad, AdaDelta, ADAM, ADAM-W, NADAM, and ADAMAX. Weight decay has little effect on SGD's convex minima. SGD Momentum's sharp minima tells us a different story, where the weight decay may be excessive. RMS Prop's sharp curvatures with high losses show low flatness, whereas AdaGrad and AdaDelta's gentle slopes show good flatness, meaning that it's more robust. ADAM is quite sensitive to steep slopes, and ADAM-W with its decoupled weight decay is more jagged and erratic. N-Adam has an extra local minima and ADAMAX has non-robust narrow zones. Our conclusion was that ADA delta offers flat minima, which is essential for better generalization. And thank you.
Thank you.